Okay, my tablet's giving me a little trouble, so we're going to do this one in two parts. So this is problem 7.6, and what we're looking at is food moving through a dryer. So what you'll see here is that we have our initial temperature at T1 equals 70 degrees Fahrenheit, and our final temperature is TF equals 170 degrees Fahrenheit. This represents the dryer, so I'll just write that in there. And what we know is, well, let's just read the problem statement. In preparation, a food product with specific gravity of 1 contains 70% water and is to be dried at 170 degrees Fahrenheit down to a moisture content of 8%. The initial temperature of the product is 70 degrees. Estimate the energy required for drying per pound mass of the original product. Express your answers in BTUs per pound mass and kilojoules per kilogram. Assume a specific gravity of 1. So what we're trying to find here is we're actually trying to find this Q. How much heat does it take to bring our temperature from 70 degrees to 170 degrees for a 1 pound mass piece? So we're not trying to look at 50 pounds or 100 pounds. I guess we could. It doesn't really matter. But we're going to do this on a unit mass basis, because once you calculate that on the 1 pound mass basis, you can just multiply the whole thing by whatever your units are or however big you want your process to be, and you multiply the heat by the same, and they scale. So how do we do this? Some of the other things that we need to know are that our kinetic energy and our pressure energy are equal to 0, and our pressure change is also equal to 0. So that allows us to simplify our energy equations. Some other things that we can figure out from this are that because mass is conserved, our total mass is going to be the same. So mass in equals mass out. And in this case, because the mass of our solids is going to be the same, our mass of solids in is equal to our mass of solids out. We're going to use that. We also know that our mass of vapor going in is equal to 0. So we can use that too. So really, the only thing that's going to change in this problem is the mass of the liquid. And what's going to happen there is we're going to use heat to take some of this liquid, and some of it is going to stay as liquid, 8%, and some of that is going to turn into vapor. Some of the other things that we can use, from our text, we know that our C solid is equal to 0.2 BTUs pound mass per degree Fahrenheit. This is on page 99. There's a picture of a banana there. You can find it. We also know from the text and from our tables that at Ti, our H sub liquid, or our initial enthalpy for the liquid is equal to H sub F, and that's equal to 38.1 BTUs per pound mass. Our TF, at our TF, then we have the same sequence, except now, because the temperature's higher, we're at 138 BTUs per pound mass. So let's talk about how we're going to do that. For conservation of mass, we're going to have our mass of solids in. So mass of solids plus mass of liquid equals 1.0 pounds, right? Now, from our exit conditions, we know that 0.08 is equal to mass of liquids at the exit divided by mass of solids at the exit plus mass of liquids at the exit. So we have this nice little equation here. Because of the other information that we've been given, we know that the mass of liquid at the exit is equal to 0.08, our final moisture content, divided by 0.92 times mass of solids at the exit, and that is going to be equal to 0.0261 pounds mass. So the mass of solids at the exit comes because we know what the mass of solids at the inlet is. And since water is conserved, now we can calculate the mass of the vapor at the exit. And that's equal to mass of liquid in minus mass of liquid out. And that is equal to 0.7 times, or sorry, not times, 0.7 minus 0.0261, and so your mass of vapor is 0.6, call it 0.67, right? So that's how many pounds of mass we've lost through that. Now that we have our mass balance done, mass balance is complete. Now we can move on and do the energy balance. So to do the energy balance, what we need to do is we need to go to conservation of energy. So this is where our equation gets kind of long, and I'm going to help you set this up, but I'm not going to solve it for you. So what we have is we have our mass of solids in times HSI plus mass of liquid in times HLI plus Q. And remember, this is what we're solving for, equals mass of the solids out, H solids out, plus mass liquids out, times H liquids out, plus mass vapor out times H vapor out. And you should be able to find all of these in your text. So how exactly do we get there from here? This is the basic form of the energy equation right here. It's broken down a little bit. But like I said earlier, we're really trying to solve for Q. So if we rewrite this so that we can do that, then what we'll end up with is that Q is equal to mass of the solids in times C solids times T exit minus T inlet plus V times P exit minus P inlet plus mass of liquid exit times H liquid exit plus mass vapor exit times H vapor exit minus mass liquid inlet times H liquid inlet. Remember what I said about pressure? So with no pressure change, this whole term goes to 0. So we can get rid of that. And that gets us to a point where we can start plugging in all of those values that we had and actually solve for Q. So what I recommend you do is go ahead and solve for Q based on that equation, and after you're done with that, then you can convert it from BTUs per pound mass to kilojoules per kilogram, and you should be good to go.